Today we will discuss what are coupled oscillators. A real physical object can be regarded as large number of simple oscillators coupled together, atoms and molecules, for example in solids. But the question is, how does the coupling affect the behavior of each of the individual oscillators? Two identical pendulums. We have two identical pendulums of length L for which we considered small oscillations. In order to find that, what is the simplest motion, we imagine two experiments. Let us take the first one. If we draw the two masses aside some distance and release them simultaneously from rest, they will swing in identical phase with no relative change in position. The spring will remain unstretched and will exert no force on either of the mass. Now we call this vibration pattern the first mode of vibration of the system. The other obvious way of starting a symmetrical oscillation will be to stretch the spring from both the ends. If we release the masses from rest simultaneously, we may notice that the spring now exert forces during motion. From symmetry of motion A and B, their positions are mirror images of each other. We call this vibration pattern the second mode of vibration of the system. Now note that each pendulum in the one of the modes above oscillates with the same frequency, the normal oscillation frequency. The two oscillating patterns are called normal modes. Both are simple harmonic motion of constant angular frequency and amplitude. General motion as superposition of normal modes. We take two coupled pendulums, identical, each starting from rest. Any motion of the system showing no special symmetry may be described as a combination of two normal modes of oscillations. We assume small displacement from the equilibrium position, that is x1 and x2 for both the masses. Each pendulum swings because of the combined force of gravity mg and the string tension T. The combined force is mg sine of theta or mg theta 1. Since theta is very small, mg over L into x1. I form the diagram if you see that the value of sine theta. But force along the spring exerted by the mass 1 is F1 minus mg theta 1 cos of theta 1 minus mg q1 minus mg x1 over L, that is the length of the string. mg sine theta 2 for mass m2, but force along the spring exerted by the mass m2 is F2 minus mg q2 cos of theta 2 minus mg q2 minus mg x2 divided by L. Displacement from the equilibrium are very small. Therefore, the angles q1, q2 are very small, hence can be approximated as sin q1 approximately q1, cos q1 approximately 1, and the displacement x1 is equal to L theta 1 and the x2 is L theta 2. If we consider x1 is not equal to x2, the spring is stretched by x2 minus x1 and the elastic restoring force in the spring will be k into x2 minus x1. The total restoring force on the mass m1 will be minus mg x1 over L minus k into x2 minus x1. Similarly for 2, it will be minus mg x2 upon L plus k x2 minus x1. Equation of motion can be written for each of the masses by using Newton's second law of motion, that is F is equal to mass into acceleration. So we can write the two equations like this: m d2x1 over dt square equal to minus mg x1 over L plus k into x2 minus x1. Similarly for the second, m d2x2 over dt square is equal to minus mg L over x into x2 minus k x2 minus x1. Let us call them equation number 1 and 2. The symmetry method to solve the system of second order differential equation. Now let us take the two equations like this. Now we can write the two equations are symmetrical, so we add and subtract them. So on adding and subtracting we get these two relations. We obtain equations that look like simple harmonic motion. We have obtained independent oscillations in x1 plus x2 and x1 minus x2. So we solve for x1 plus x2 and x1 minus x2. So let us say x1 plus x2 is a cos of omega t, x1 minus x2 is b cos omega t, where omega is equal to under root of g by l for 1, and for second it is under root g by l plus 2k over m, where omega and omega s are called as normal frequencies. In writing the solution, we need to apply the initial conditions. For this, we have to distinguish between the two oscillating patterns. First is parallel oscillations. If you see this diagram 1 and 2, symmetrical oscillations. For parallel oscillations, let b is equal to 0, x1 minus x2 is equal to 0. The two pendulums are moving in parallel. The spring does nothing as if didn't exist. They both oscillate with omega p, the natural frequency of free pendulum, without coupling. This is the first normal mode of oscillation. The second is symmetrical oscillation. Let a is equal to 0. So x1 plus x2 is equal to 0. The spring gets expanded, shrunk by twice the movement of each pendulum, so that omega s is equal to under root g over l plus 2k by m is determined by both the pendulum and the spring. Each pendulum oscillates with a frequency omega s, but they are out of phase by pi. This is the second normal mode. Now, the general solution of the system of differential equation is a linear combination of normal modes. So let us take x1 and x2 like this: a by 2 cos omega pt plus b by 2 cos omega st. Similarly, for x2, it is a by 2 cos omega pt minus b by 2 cos omega st. We need a solution that satisfies an initial condition. Let us use an example. Now, if you choose this example, in one case, that first spring, that one object is to the right, but the second is in the fixed position. Initial condition for the two masses, x1 a, x1 at 0, it is dx1 over dt is equal to 0, and x2 is equal to 0, and x2 dot is also equal to 0. So we get the two relations, a and capital A and capital B, which is equal to small a, which results in the following equations, which are the solutions. x1 is equal to a by 2 cos omega pt plus cos omega st, and x2 is equal to a2 cos omega pt minus cos omega st. The two normal modes are x1 plus x2, first lower mode, x1 minus x2, which is a cos omega st, second higher mode. Now we define, let q1 is equal to x1 plus x2 and q2 is equal to x1 minus x2, the normal coordinates of the system. If we use cos alpha plus cos beta, which is equal to twice of cos of alpha plus beta by 2, cos of alpha minus beta by 2. So cos alpha minus cos beta is also equal to that. Using these relations, we get that two values x1 and x2 are the two individual oscillations. If omega 1 p minus omega s is very small as compared to omega p plus omega s, the spring constant is very small and the coupling between the two pendulums is very weak. So omega p and omega s, which are called as two normal frequencies. We notice that in each normal mode, the individual oscillators oscillate with the same normal frequency.